This diagram shows the process of gaseous exchange by bringing oxygen into our bodies and getting rid of carbon dioxide by diffusion, which is very different at sea level compared to altitude. At altitude, the atmospheric pressure is lower than 96 mmHg compared to 159 mmHg at sea level. This means that there's less difference in the air pressure outside our bodies and in our lungs at altitude than there is at sea level. The difference in pressure is what drives the air into our lungs, so we take in less air. Once the oxygen has got into our bloodstream, the diffusion gradient begins to between the blood and the muscle is lower at altitude. The diffusion gradient is 60 mmHg at sea level and only 15 mmHg at altitude. This means that the difference in concentration levels of oxygen is much greater at sea level compared to altitude, so more diffusion takes place at sea level than at altitude. Therefore, at altitude there is less oxygen for aerobic metabolism. This means that our bodies will have to work harder to get the oxygen to our working muscles at altitude. In response, our bodies create a chemical called erythropoietin, and this makes our body increase production of red blood cells and carry more oxygen. This diagram shows how our VO2 max is reduced at altitude. As the altitude increases, the VO2 decreases linearly. There is less oxygen able to be breathed in at altitude, so the maximum amount of oxygen your body will be able to use is going to be less than that at sea level, where more oxygen can be breathed in. The symptoms of altitude sickness are nausea, vomiting, shortness of breath, and insomnia. It happens between 6 to 96 hours after arrival at altitude and may be caused by a build-up of carbon dioxide in the body as it struggles to get rid of it due to the change in air pressure. To avoid getting altitude sickness, it's a good idea to limit how far you ascend each day by 300 meters. There are two types of altitude sickness. The first one is high altitude pulmonary edema, or HAPE. The symptoms are shortness of breath, excessive fatigue, blue lips and fingers and nails, and mental confusion. This happens because there is a build-up of fluid in the lungs, which stops the air being able to diffuse and move around the body. It will occur if you ascend too quickly above 2,700 meters. The treatment is to give oxygen to the patient and move them to a lower altitude. Another type of altitude sickness is high altitude cerebral edema, or HACE. This happens at high altitude above 4,300 meters, and the symptoms are more severe, including mental confusion, progressing to coma and death. It happens because of a build-up of fluid in the cranial cavity. Treatment is giving oxygen to the patient and moving them to a lower altitude. Altitude has a negative effect on endurance sporting performance. Athletes can't reach as high a VO2 max, and they fatigue more quickly because when the athlete is working not at their maximum heart rate, they will start to feel worse than they usually do. This can cause them to do worse because they feel worse. Also, muscle gain does not happen as easily at altitude. There is also a decrease in the alkaline reserve, which maintains a healthy blood pH. Endurance athletes are the most affected by altitude because they rely on the efficient transport and diffusion of oxygen to power their aerobic energy system. Sprinters, on the other hand, are working anaerobically without oxygen, so it doesn't affect them as much. The height at which an endurance athlete's VO2 max will be affected is 1,600 meters. After this point, VO2 max decreases by 11% for every 1,000 meters. Some athletes benefit from the high altitude, such as in jumping and throwing events, because there's less aerodynamic resistance and less gravitational pull in the thin air. For instance, Bob Bierman broke the long jump world record at the 1968 Mexico Olympic Games. The altitude was 2,200 meters, and this made the air pressure lower, which allowed him to travel further through the air. His record stood for 27 years. Many athletes are using altitude training to help them improve performance. There are 3 types: live high, train high. Everyone knows that Kenyan and Ethiopian runners have dominated long-distance marathon running and athletics for many years. This is because their bodies have adapted to be able to exercise with a reduced amount of oxygen, making their aerobic systems incredibly efficient. Live low, train high. Athletes such as Mo Farah have seen the advantage the Kenyan and Ethiopian runners have experienced due to altitude training. He spends months away from his family training in Kenya's Rift Valley to achieve the same adaptation. Live high, train low. The theory is that living at high altitude allows your body to make adaptations, while training at a low level allows you to train hard, which you couldn't do at altitude unless, like the Kenyans, you were fully adapted. Research has not shown any performance benefits. In a study, Dr. Robert Chapman found that some people respond well to altitude training and some did not. It seems to depend on a specific type of EPO gene, so whilst altitude training can be very effective, sometimes it doesn't work for everyone. People have tried to simulate the effects of altitude training using tents or masks to decrease the amount of oxygen breathed in by the athlete in order to promote the production of red blood cells. Many athletes have used these tents, such as Michael Phelps. However, research shows that athletes using these tents and masks exhaled less nitric oxide than those doing real altitude training. Nitric oxide is linked to vasodilation in the veins and is thought to be one of the reasons that altitude training is effective. However, the effects of altitude training only last for 15 days, so tents and masks are more practical. Masks don't change the partial pressure of the air or the amount of oxygen breathed in. They simply reduce the amount of air going into the lungs. They therefore have the effect of making your respiratory muscle stronger, but they don't promote the production of any red blood cells.